That's what we are going to study in this module 2. Again, it is a very simple module as far as your examination is also concerned, right? So before we go into the Carnap map or K-map, we'll quickly revise the concepts of digital electronics, which you already studied in your previous courses like pre-university course or in first year engineering level, right? So we'll this is a reference book, as I already told, Charles H. Roth and Larry Kinney, and that is the textbook you have to refer for this particular subject, that is 2019 edition, which covers entire syllabus. All the 5 modules are covered in this particular book, right? So quickly we'll revise the fundamental things related to the digital electronics. So already you have studied what is digital electronics. Can anybody define what is digital electronics? Yes? Can anyone define what exactly you mean by digital electronics?
Processing of discrete signals.
Processing of discrete signals. No. Can anybody give me a proper answer? What exactly you mean by digital circuit or a digital system?
It is a field of electronics in which the study of digital signals we are going to.
Field of electronics, wherein study of digital signals. Any other definition? Yes? Yeah, what exactly you mean by digital electronics? Yes, quickly, because we have to revise all those things and then we proceed further. Yes, basically digital electronics or study of those logic circuits which follows 2 states of operation, right? The study of digital circuits which follows 2 states of operations, we can call it as like a digital electronics. And the 2 states can be represented as either high, low, on, off, true, false, 0, 1, etc. Right? So to represent these 2 states of a digital system, we need 2 voltage levels. Right? So 2 voltage levels are required to represent the 2 states of a digital system, and based on what voltage levels we use to represent the 2 levels of a digital system, we have 2 different types of digital systems. Those are called as positive logic digital system and negative logic digital system. In positive logic digital system, higher voltage is used to represent high state and lower voltage is used to represent low state. Whereas in negative logic digital system, it is opposite. That is, high voltage is used to represent low state and less voltage is used to represent high state. For example, normally we use 0 volt and 5 volt, right, in most of the cases. So if you use 5 volt to represent logic high and 0 volt to represent logic low, then that system is called as what? Positive logic digital system. On the other hand, if you use reverse, 5 volt is used to represent low level and 0 volt is used to represent high level, then that system is called as what? Negative logic digital system. So there are 2 different types of digital systems: positive logic digital system and negative logic digital system. And the basic building block of all the digital system, whether they follow positive logic or negative logic, is the basic gate. So that is the logic gate. Now, what do you mean by a logic gate? Yes, any answer? In fact, it is there. I have mentioned in the slide. What do you mean by a logic gate? A logic gate is basically a digital circuit with minimum 1 or more than 1 input and only 1 output. Right? So here I have mentioned voltages because, as I just now told, every input should have certain voltage. Only 2 levels of voltages we are using. So logic gate is a digital circuit with 1 or more inputs and only 1 output, and the output depends upon the combinations of the input given to that particular circuit. Such a digital circuit is called as logic gate. I hope the definition of logic gate is clear. Yes? Yeah, someone should unmute and you can say yes, because since I am sharing my screen, I will not able to see the chat box right now, because once the screen, I am in screen share mode, it is not possible to go through the chat box, right? Okay.
Yes, sir.
Yes, logic gates are the fundamental building blocks of a digital system, which I already told. And there are various logic gates, which can have one input or more than one input, but there is only one gate which is having single input, and all the other gates which we'll be studying, they will have minimum two or more than two inputs. So different logic gates, the input and output combinations are listed in tabular form, and the input output relationship is also mentioned, and that tabular form or a table which lists out all possible input output combinations of a digital circuit is called as what? What it is called as? Yes?
Truth table.
Truth table, yes. Right? So we'll study now one by one what are the different gates. This already studied. I'll not spend much time here, but you should know what is that gate, what is its truth table, what is the timing diagram, and it is available in the integrated circuit form, and what is the IC number for that particular integrated circuit, because you are going to perform the laboratory experiment also on this, so there you should be knowing this integrated circuit, that is IC numbers, and using that particular IC number you will able to do the experiment in the laboratory of this subject, that is analog and digital electronics laboratory. So the first basic gate that we will be studying is called as a NOT gate, which is also called as an inverter. So what is a NOT gate or an inverter? As I told, it is a gate with only one input and a single output, and the output will be complement of the input. Whatever input you give, a complement of that you are going to get as the output. So that gate is called as a NOT gate or a inverter, whose circuit symbol or a logic symbol is as shown here. You can see here, this is the circuit symbol of the NOT gate, right? Is it visible? Just a minute, sorry. Yes. It's a highlighter I have taken. Yeah, this is the symbol of what? The NOT gate, where you can see that it is having a single input. This is A is the input and Y is what? Output. And how the output inputs are related? Here output Y is written as Y is equal to, right, complement of what? A. So Y is the output, A is the input, so Y is equal to complement of A, that is the NOT gate. So here the truth table is shown, A input, Y output. So the inputs can be represented by 0 and 1, normally what we do, but if you want, it can be represented in terms of low and high also. L means low, H means high. But we'll be following this particular sign convention. 0 indicates low, 1 indicates high. So when A is 0, you can see here Y is 1, and when A is 1, Y is 0. So this gate is called as what? A NOT gate or an inverter or a complementer. Now you can see here, one input symmetrical square wave is shown, which we can normally call it as a clock signal, right? So if you give this as pin 1 means input, if this is the input given, what output you are going to get at the pin number 2, you can see here, when the input is 0, output is 1. Similarly, when input is 1, output is what? 0. Then again it repeats. So such gate is called as a NOT gate. right? So this NOT gate or inverter is available in integrated circuit form. What is the IC number? Which is a 8-pin dual in line package IC. Sorry, 16-pin dual in this particular NOT gate 7404. So sorry, 14-pin dual in line package IC, which consists of 6 NOT gates in a single IC. So 7404 is an integrated circuit which is 14-pin IC which consists of 6 NOT gates in it. So you can see here pin number 1 is the input to the NOT gate 1 and pin number 2 is the output. So this is one NOT gate you can use. Similarly 3 and 4 can be used as one NOT gate, 5 and 6 as another NOT gate, then 9 and 8. Here 8 is the output, 9 is input. Similarly 10 is the input, 11 is 10 is the output, 11 is the input, 12 output, 13 input. So we have 6 NOT gates along with 2 pins which are used. Pin number 7 is used for ground and pin number 14 is used for VCC. Ground means 0 volt, VCC means 5 volt. So if you want to use a NOT gate in your laboratory, you have to use this particular IC, that is 7404, which consists of 6 NOT gates in it. If you need more than 6, then you can use such 2 ICs. Depending on your requirement, you can use a number of ICs and you can see the functioning of that particular gate. That is what is called as a NOT gate. I hope it is clear. Any doubts here? All of you understood? Already you know this. Only thing you should know here is this part. This is the integrated circuit chip, IC chip, which you will be using in the laboratory, and what are the pin configurations of that you should know. And this is called as the timing diagram for that particular NOT gate. Any doubts here? See, there should be response from your end, otherwise I will not able to make out whether you are following it or not.
No, sir.
No means you have not understood.
No, sir.
No
I have
doubts.
understood. No doubts. Sir.
Okay, fine. Then we'll move on to the next gate, right? So I'll not spend much time. I actually already, you know, quickly we'll see these gates. What is second gate here I have mentioned? It is AND gate, right? This is a gate with 2 or more than 2 inputs. You can see there I have shown 2 different gates. The first one, this is having how many inputs? This gate is having how many inputs?
2 inputs.
2 inputs, A and B, and single output Y. Similarly, this is having how many inputs?
3.
3 inputs.
3 inputs A, B, C, and single output Y. These are the symbols of AND gate, which can have 2 or more than 2 inputs and single output. And the important characteristics of the AND gate is that the output is high only when the output is high.
All the inputs are high.
Even if one of the inputs is low, output will be low. That's what is shown in the truth table. This is truth table for 2 input gate. This is truth table for what? 3 input AND gate. You can see in the truth table, when we have 2 inputs, how many input combinations we will get? Because every input can take 2 values. So
4
inputs will get 4 combinations. What are those 4 combinations? 0, 0, 0, 1, 1, 0, 1, 1. So we'll not get any other combination with 2 inputs. And from these 2 inputs, we have 4 combinations. And you can see the truth table. Out of the 4 combinations, first 3 input combinations gives you output as what? 0. And the last input combination where both the inputs A and B are 1, the output Y is high.
1.
Is that clear? Similarly, if you see the 3 input, with 3 inputs, how many input combinations we are going to get?
8.
8, because 2 to the power 3 equal to 8. What are those 8 combinations? From 0, 0, 0 to 1, 1, 1. And you may be knowing how this can be written. Here C, we call it as like LSB, A is the MSB. LSB changes at every interval, you can see. 0, 1, 0, 1, 0, 1, 0, 1. Right? This part changes at every instant. That is 0, 1, 0, 1. Whereas second bit B, it changes what? How? 2 zeros, then 2 ones, again 2 zeros, and 2 ones. And the third bit, you can see there are 4 zeros and 4 ones. Like this, if you write, you will cover all the 8 input combinations. Suppose if I add here one more input, say X, then how do you write it? This should change 010101, second 00110011, 4041. Here what you should get now? If you add one more, 80 and 81. So totally how many combinations you will be getting there? If you add one more bit, how many input combinations you are going to get? 2 to the power 4 equal to how much?
16.
With 3 we have 8, and with 4 you will get the 16, and with 2 we have 4. So this is what is AND gate, and in both these truth tables you can see that all the input combinations will give 0 output except for only one combination, that is the last combination where both the inputs are high, output is high. Here all the 3 inputs are high, output is high. So this gate is called as what? It is called as what? AND gate. Right? So like all other gates, this AND gate is also available in integrated circuit form. Before that, you can see here a timing diagram is shown. So one random square wave is taken like this, wherein this is 0, this is 1, 0, 1, 0. This is one input. Then here this is 0, 1, 0, 1, 0, 1, and so on. Right? These two are the inputs. Now, how do you write the output? Wherever input changes, you have to check what is the output at that interval. So here you can make it vertical lines like this. Wherever the input is changing, you should have the vertical line so that easily you can draw the output. Now you have to say, wherever you have drawn the vertical line, what are the inputs you have to check? What is this input A here? This is first input. What is the value of that? 0.
0.
What is the second input?
0.
0. So what output you should get?
0.
0. So you can see here you have got 0. Similarly here, for this portion you should check what are the inputs. What is first input?
0.
Second input?
1.
What is the output?
0.
Then for this portion, what is the first input?
1.
1.
1. Second input?
0.
What is the output?
0.
0.
Now for this portion you can see, what are the inputs? What is first input?
1.
1. Second input?
1.
1.
What is the output?
1. 1.
I hope it is clear how to draw the timing diagram.
Yes, sir.
Because timing diagram plays a very important
Yes, sir.
role in digital electronics. Any doubts in drawing the timing diagram? So you can take any random like square
No,
wave
sir.
like this, right? Another one you can have like this, and you can consider this as input A, this you can consider as input B, and then you can write the output Y for this. So I told how to draw the vertical line wherever any of the input changes. So here it is changing, you draw like this. Here it is changing, right? Then maybe, yes, here it is changing again. Then it is changing here, here, like this. Vertical lines you should draw first. And for that, each of the vertical portion, you have to check what is the output. Now, can you tell me what is the input A here?
0.
0. Here?
0.
So what should be the output?
0.
0.
0.
0. Then next here, what is the input A?
1.
1.
B?
0.
B is 0. So what should be the output? 0.
0.
So for this portion, what is A?
1.
B?
1.
1.
So what should be the
One.
output? Y?
1.
1.
1.
1.
Now here, for this portion, A is
0.
0. B is
1.
1. So what should be the output?
0.
0.
0. Now
Zero.
here both are 0. So output should be
0.
0.
0.
Here this is 1, this is 0, out 0.
0.
Like this, you have to draw the timing diagram. I hope it is clear. Any
Yes,
doubts in drawing the timing
Yes.
diagram for any logic gate?
No, sir.
No, sir.
Yes, clear.
No, sir.
So this AND gate is up because these all things you know, but important thing is again this. What is this called as? What is this diagram I have shown? It is called as the pin diagram of IC
Integrated
what?
circuit.
Pin diagram.
Integrated
IC?
circuit.
740.
IC what? 7408. So 7408 represents what? 7408 represents AND gate.
And
7404 represents what? Just now we have seen. IC 7404 is
Not
what?
gate.
Not
Not
gate.
gate.
Whereas
not gate.
7408 is called as
AND gate.
AND
AND
gate
gate.
IC.
And
It is
AND
again
gate.
14 pin IC. Out of 14 pin, 2 pins will be used for ground and VCC. Pin number 7 is ground always. Pin number 14 is VCC. So
VCC.
remaining 12 pins are available. Right. So with 12 pins, how many gates you can get? Because every gate requires how many pins here?
3 pins.
Every
So
gate
4.
requires 3 pins, 2 for input, 1 for the output. So with total 12 pins, how many gates you can include in this IC?
4.
4.
4.
That's why you might have seen there how many gates you were having? In the
Six.
previous 7404, 6.
6.
Why you were having 6 gates in one IC? Because
Only
there we
one
were
in
requiring
one.
only 2 pins for
2 pins.
each gate.
Yes.
But here we need 3 pins for each gate. So number of gates here are less. So every 7408 IC will have how many gates? 4 AND gates. So if you want to use any AND gate out of this IC, you can use these pin numbers 1, 2, 3 for one gate, 4, 5, 6 for second gate, 8, 9, 10 for the third gate, 11, 12, 13 for what? Fourth gate. So if you are using this down portion, 1 and 2 is input, 3 is output. Similarly, if you want one more gate, 4 and 5 is input, 6 is the output. Whereas here you can see in the above portion, 8 is the output, 9 and 10 is the input. Here 11 is the output, 12 and 13 is the input. Then you may ask the question, why the numbering is given like this? That we can't change this numbering because these are the pin configuration provided by the manufacturer of that particular integrated circuit or IC. So we should remember these pin diagrams or pin numbers, and accordingly we can use these ICs for constructing any digital circuit. I hope the second gate is also clear.
Yes, sir.
Yes, sir.
Or
Yes, sir.
that is NOT gate and the AND gate. Now quickly we'll move on to the third gate. In fact, the slides are more explanatory there. You can see what is OR gate. This is a gate with what? How many inputs? 2 or more than 2 inputs and only 1 output. And when the output will be high here? Output of the OR gate will be high when
one of the input
even
is
if
high.
one
One
of
of
the
the
input is high, or output of the OR gate will be low only when what?
Both the inputs are
Both
low.
are
All the inputs. Don't call only both. Don't make it specific to only 2 input AND gates. You may have a 2 input OR gate. You may have 2 input gate. You may have 3 input. You may have 4, 5 also. So in general, output of the OR gate will be low only when
All the inputs are low.
all the inputs
all
are
the inputs are low.
Low.
Even if one of the input is high, output will be high.
High.
That's why you can see this is a 2 input OR gate, truth table for 2 input OR gate. This is 2 input OR gate symbol, and this is its truth table. This is 3 input OR gates, truth table for 3 input OR gate. You can see only first input combination where all inputs are low. Here both the inputs are low, so output is low. Here all 3 are low, so output is low. Whereas for rest all input combination, either 1, 2 or all the inputs will be high, so output is what?
high.
Output is high. As such gate is called as OR gate, right? So this also again is self-explanatory. What is the IC number? You have to remember here for OR gate, 2 input OR gate. IC number is what? 7432.
7432.
So how many gates it is having again?
4.
4.
Why it is having only 4 gates?
3 pins are
Because
It is 3 pins.
number of pins are fixed. Each IC is having how many pins?
3 pins.
3 pins.
No, how
3.
many pins each IC? Each IC is having totally 14 pins.
14.
Out of 14, 2 are used for VCC and ground. So remaining pins are how many?
12.
12. So each requires 3. So 12 divided by 3, how many gates we can have?
4.
4.
4. So here also we have 4 OR gates in the IC 7432. Is that clear? Any doubts in the timing diagram?
No,
Again, I told you how
No,
to
sir.
draw the timing diagram. Every time you make a habit of having the vertical lines like this. Wherever input changes, if you draw the vertical lines like this, dotted lines you should draw, and then you can see the what are the inputs for this. Right? Just check what are the inputs. Sir, I am having class. I call you up to tell me. Right? So here, this is the input low. This also is low. So what is the output? This input, first input is low, second input is low. So what is the output?
Low.
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 Similarly, first input here is low, second input is what?
High.
High. So what is the output for this portion?
High.
That's what, when you are drawing the timing diagram, one very important thing you should remember. You should not bother about what is that input or output for the entire duration. When till a particular point where one of the input is changing, for that particular duration, you should check all the inputs. And based on that, you should write the output. I hope writing timing diagram, there should not be any problem. Any difficulty in writing or drawing the timing diagrams?
No, sir.
Okay,
No, sir.
fine.
No.
So we'll move on to next gate then. Because quickly
Yes,
I
sir.
want to review all these basic concepts today. Next, you can see what is this gate?
NOR gate.
NOR gate. What is NOR gate?
Complement of
Or
OR gate.
followed by NOT. Or just now we have studied OR gate. Right? This is what we have studied, the OR gate. You can see the symbol of the NOR gate. Right? OR followed by NOT gives you what? NOR. This is the symbol for NOR gate. What is the difference between symbol of a OR gate and a NOR gate? Can anybody tell me the difference between this symbol of OR gate and the NOR gate?
Circle in front of gate.
That is, there is a bubble.
Bubble.
We call it as a bubble. So whenever you see a bubble, one thing you should remember, bubble indicates complement. Right? Bubble is like putting a bar on the variable. Is that clear? So if without this bubble, it becomes A or B. So with this bubble, it becomes what? Normally we write A or, sorry, B like this. Right? Y is equal to A or B. Fine. NOR gate, how do you write? You have to put a bar like this. A plus B whole bar is called as a NOR gate. You can see the truth table. It is a complement of OR. How we have written truth table for OR gate? 0, 1, 1, 1. Whereas truth table for NOR gate is what? 1, 0, 0, 0. How you should write it? Simple way I will tell you. First you should do the OR operation. What is 0 or 0? Yes?
0.
0 or 0 is 0. So write complement of that. What is that? 1.
1.
Similarly, what is 0 or 1?
1.
0 or 1 is 1. Complement of that is 0.
0.
1 or 0 is 1. Complement is 0.
0.
1 or 1 is 1. Complement is 0.
0.
This is how you can write the truth table for NOR gate. Now, we have a IC. What is the IC number you can see here now for NOR gate?
7402.
7402. And you can see here slight different arrangement of the gates. Again, every gate requires how many pins? 3.
3.
So we can have 4 gates only. Pin number 7 is for ground, pin number 14 is VCC, and we have remaining pins used for the 4 gates. But how you can see now inputs and outputs are assigned. So far for all the gates we were having what? 1 and 2 as the input and 3 is the output. But here you can see now 2 and 3 input and 1 is the output. Similarly, these two are input, this is the output. And here you can see now 8, 9 input, 10 output. 11, 12 input, 13 output. So this is the IC 7402 NOR gate, 2 input NOR gate IC. Hope it is clear.
Yes, sir.
Then this NOR gate is called as a universal gate actually. Right? Why NOR gate is called as a universal gate? Because using only NOR gate, you can construct the 3 basic gates. There are 3 basic gates, AND, OR and NOT, which we have studied. And NOR is called as a universal gate. Why NOR is called as a universal gate? Because all the other basic gates can be constructed using only NOR gate. Now, if you see this first, what you can see here in this, what are the 2 inputs to this NOR gate? What are the two inputs given to the NOR gate?
A
What?
and A only.
A and A only. So what output you will get? A
A.
plus A, what? Whole bar. Actually, NOR gate gives the complement of OR, A or A whole bar. But shortly we will be studying one property. A or A gives you what? A. So it becomes what? A bar. So if you give A input common to both the inputs, you will be getting A bar. So if you use NOR gate like this, it acts as a what? It acts
Not
as a
gate.
what?
Not gate.
Not.
Okay.
Similarly, if you want to implement, say, OR gate from it, what you can do? What is this portion now? This is what? A
B.
plus B whole bar, which we call it as a NOR. Is that clear? But I want A plus B from this. How I should get now? Because OR means I should get only A plus B. How we can obtain A plus B? We have to remove this bar. How we can remove this bar? Simply I will use eraser and remove this. Done?
We
So,
should draw one second.
to remove this bar, you give
Another NOR
that
gate.
output to what? One NOT gate. This is a NOT gate, but you should not use simple NOT gate. You have to construct that using what? NOR gate only. So this is NOR gate. Output of NOR gate, if you give it to the NOT gate, what you are going to get is OR, that is A plus B. Similarly, if you want to get AND, that is A dot B, what you should do? Give A, get A bar, then get here B bar, and this A bar and B bar, if you give here, we'll get it as A dot B. You already studied De Morgan's theorem. A bar dot B, A bar plus B bar, actually you will be getting it as A bar plus B bar whole bar. This can be written as what? How do you write it? A double bar dot B double bar. Because you have this, no, if you want to remove this complement, you have to change this from plus to dot, right? And then you have to take the individual complement. A bar is there, make it A double bar. B bar is there, make B double bar. Then double bar vanish, and finally you get what?
A.
What is it? A dot B. So this is how we can construct AND OR and NOT gate using only NOR gate. Hence, NOR gate is called as what? What is called as?
Universal gate.
Universal gate. Right. Then we have one more gate called NAND gate. What is NAND? It is self-explanatory. I need not explain much here.
Combination of
This represents AND gate followed by an inverter. So this is AND gate. To this AND gate, if you add one inverter, you get what is called as what? NAND. So AND with the bubble is called as this. Normally, AND gate is written like this: A dot B. Whereas NAND is written as what? A dot B whole bar. Is that clear? A dot B is called as AND. A dot B complement is called as NAND. How do we write the truth table? You can see. What is 0 and 0?
0.
Complement of that is 1. 0 and 1?
0.
0.
1. 1 and 0?
0.
Complement is 1. 1 and 1?
1.
1.
And
Complement is 0.
0.
This is the truth table for NAND gate. And you can see this is the what is that? Integrated circuit for the NAND gate, which is similar to your AND gate. Every gate requires 3 pins. So 1, 2 are input, 3 is the output. Anyhow, all these pin diagrams will be available in the laboratory. When you do the experimentation, you can refer those pin diagrams, and accordingly you have to construct the circuit, right? That is about the NAND gate. How we have shown NOR as a universal gate, here NAND also can be shown as a universal gate. Again, you have already studied this. You can just go through this slide. This is called as universal property of the NAND gate. Right? By sorting both the inputs, we can get NOT gate, and giving the output of a NAND gate to NOT gate, we can get AND gate, and giving each input complemented form to the NAND gate, we can get OR gate. This is OR gate, this is AND gate, and this is NOT gate. So NOT, and OR are constructed using only NAND gate. Hence NAND is also called as an universal gate. Right. Then we have a derived gate called exclusive OR gate. This is the symbol for exclusive OR gate. What is exclusive OR or XOR gate? It is a logic gate which gives you high output only when odd number of inputs are high. That's why sometimes exclusive OR gate is called as odd parity indicator. It is called as odd parity indicator. When odd number of inputs are high, its output will be high, otherwise output will be low. And this is how the exclusive OR gate is represented by symbol A XOR B. If you write plus, it is OR. If you write that plus inside the circle, it becomes exclusive OR. And this exclusive OR truth table you can see here is when both are 0 0, output is 0. Both are 1 1, output is 0. When both are different, output is 1. Then you may ask, just now I mentioned here odd number. Here how many inputs are high?
2.
How many inputs are high?
Even.
How many
0.
inputs are high, I am asking?
0.
0 number of inputs are high. How many inputs are high, I am asking, not how many inputs. There are 2 inputs, fine. But out of these 2 inputs, how many are high?
No one.
None of the inputs, 0. So we consider 0 in the even numbers. So output is 0. Similarly here, how many inputs are high?
Both the inputs are
2 inputs are high. Again we consider 2 as the even number. So output is 0. But for these 2 cases, how many inputs are high? In each case?
1.
1 is considered as what? Odd
Odd.
number. So output is 1 here. This is 1. This is 1. Now, if you want to write this output in terms of a truth table, sorry, if in terms of a Boolean expression, how do you write it? These 2 inputs gives the output high. So how do you represent this input combination in terms of A and B? Or before that, each input combination can be represented in terms of the input variables. If the variable is 0, complement of that variable is taken, and if the variable is 1, that variable should be taken as it is. And when there are more than one variables present, you have to take the AND operation. And when there are more than one outputs are high, you have to perform the OR operation. So can you tell me what is the minterm corresponding to this first input combination? A is 0, B is 0. So how do you represent this input combination in terms of the inputs A and B?
A bar, B bar.
A bar, B bar, exactly right. This second one, how do you write?
A bar
A
B.
bar, B.
A bar, B. Third one?
A B bar.
A, B bar. And fourth one?
A B.
A, B. Right? These are the 4 combinations. Out of these 4 combinations, only these 2 are high. So you should take this, and then take the OR operation. You will get what is A XOR B. What is this? A bar B. What is this? A B
A
bar.
B bar.
So take OR operation. You will get A XOR B as what? A bar B plus A B bar. I hope it is clear how you get this equation from the truth table. Is that clear? A bar B plus A B bar you are going to get from this truth table, and that is nothing but A XOR B, and this is represented using basic gates like this. You can see here it is A bar and B, one AND gate. A and B bar, another AND gate. Both these terms should be given to OR gate. You will get Y as this, and that is equal to this. So this is how you can represent like exclusive OR gate in terms of the Boolean equation, and then you can draw the logic diagram using basic gates. Actual symbol of the XOR gate is this. This XOR gate consists of this particular hardware using what? The basic gates. Is that clear?
Yes, sir.
What is XOR gate? right? So you can see here, 4-input XOR gate I have shown. Like in this 4-input XOR gate, the inputs are 1, 2, 3, 4. This is single 4-input XOR gate, or the same can be constructed using one 2-input XOR gate, another 2-input XOR gate. Both the outputs you can give to third 2-input XOR gate. You will get one 4-input exclusive OR gate. Is that clear? So you can see what are the output. How many inputs are high here for the first input combination? It's like this number represents even or odd, you have to check and you should give the output. What this represents? How many inputs are high?
0.
0. So we consider it as even, output is 0. Here how many inputs are high?
1.
1. So 1 will be considered as what? Odd. So output is 1. For the third input case, how many inputs are high?
1.
1 odd. One important thing you have to remember, we are not checking whether the entire number is even or odd. What we are checking?
Number of inputs.
Number of ones are even or odd, you have to check, not the entire number. Is that clear? Otherwise, if you would have done that, first number is even, second odd, then third even, fourth odd, even odd, we would have got. But here we are not checking whether that number is even or odd. What we are checking is whether number of ones are even or odd, and accordingly we are writing the output when number of ones are odd. Is that clear?
Yes, sir.
Is it clear? This is exclusive OR gate, exclusive NOR it is, sorry, it is not OR, exclusive NOR. XOR gate, if you put a bubble, it becomes what? It becomes what? XNOR. Now, XNOR gate is called as what? What it is called as?
Even parity indicator.
Even parity indicator. You can see difference in the truth table. When both the inputs are 0, it is even, output is high. Here also, like even, output is high. These two are low. So the output Y is represent like this. This is called as X NOR operation. And in terms of the inputs, we write it as what? A bar, B bar. And this is what? AB. So Y can be written as AB plus A bar, B bar. Or it can also be written as complement of XOR. Complement of XOR is XNOR. And the XNOR can be represented in terms of the Boolean variables A and B as A bar, B bar plus AB, and this can be implemented using basic gates. We can use basic gates like how we have done this diagram. Exactly in the same way, we can have a logic diagram drawn for this. So that is about the different gates. So here we have discussed 3 basic gates, AND or NOT. Then we have discussed 2 universal gates, NAND and NOT. Then we have discussed 2 derived gate, exclusive OR and exclusive NOT. So to summarize this, it is given here. In fact, there I have forgot to mention the pin number for IC NAND gate. It is shown here. This is just a summary of that particular those particular gates. Right? I think you have a next class now. With this, we'll stop here today. Just I have given you the brief overview of the logic gates and the digital electronics. In the next class, we'll be moving ahead with the Boolean equations, how we can represent a Boolean variable, SOP form, POS form. Then in brief, we'll see laws of Boolean algebra and all. And then we'll move to the first method of simplification called K-map method. I hope all of you understood whatever has been covered in this class, today's class.
Yes,
If you have
sir.
any queries, quickly you can ask so that you can go and attend your next class. Yeah.
No doubt.
Any doubts, any queries if you have? In
No,
fact, today I have
No,
not
sir.
covered anything new.
No, sir.
So like whatever you have studied in your earlier semester.